Hey everyone, it's JG. I'm playing Eternal Evolution, and tonight I'm ready to bust out some spreadsheets and PowerPoint to show you some things that I'm learning here. So, in any game like this, eventually you're going to find yourself asking a question like, okay, what's going to be best for keeping my character alive? Is it going to be 20,000 more HP, or 2,000 more defense, or 15% damage reduction? And to answer questions like that, you really need to understand how the damage mechanics in the game work, particularly things like the defense formula. How does defense reduce incoming damage? Usually game developers don't just publish that stuff outright, so it's up to mathematically minded players like myself to kind of reverse engineer that. So we're a good 3 weeks into this game. I figure it's time to start busting out the spreadsheets and figuring out what's under the hood here. So I did a bunch of tests over the last couple of days and started to figure out, I think, pretty well how all these mechanics work. One note, I did try to put the formulas in the video comments below, so if you need to refer to those later, you'll be able to find them there without rewatching the video every time for it. I would recommend you still watch the video because there's some finer points that you might like some explanation on, but after that, you can just refer to those formulas in the text whenever you need them. So first off, I wanted to show you what my test harness looks like. Here's how I actually performed these tests. So this is what it looks like. Here we have Jericho with no equipment and no supporting anything, fighting level 7 of the Terradome, because I can do that for free without taking any resources. So yeah, it says he's probably not going to win. I agree. And here at the beginning, here comes the boss. He throws out a little fireball, and it does 73.4 thousand damage. Okay, so we write that down in a spreadsheet, and we do it again. Try again. Here comes the boss, here comes the fireball, and then 73.9 thousand damage this time. So, essentially, I did dozens and dozens of runs for this using a variety of different heroes with different equipment, different damage reduction, different defense levels, to get a sense for just what the mechanics are in the game here. All right, so let's dive into the data. So, this is what I came up with for my very first plot of a number of different runs, comparing damage taken versus defense. And there's a couple things that I noticed right off the bat. Number one, this spread for a given defense level was reliably right around 4%. So this is the random factor for damage in the game. So the difference between the weakest hit that I ever observed and the strongest hit that I ever observed in any given setup got as high as about like 4.05%. On the low end, I'd see about 3.7%. That was probably just that I didn't do enough samples to hit the very highest or very lowest value. But yeah, something in the ballpark of 4% is the amount of randomness that happens in damage in this game. So that's a useful number to be aware of, if it makes sense. The second thing I noticed was here I was sort of trying to undo the effect of damage reduction, assuming that I knew how that worked, but found that up here at higher defense levels, I actually had a place where I was taking more damage at higher defense after accounting for damage reduction, which kind of surprised me. So what I recognized here was, although I assumed that damage reduction would work in a certain way, it turns out damage reduction does not work that way. That was one of my very first discoveries. So here, the red dots here are the amount of damage reduction that it says that you have, 10%, 20%, something like that. The blue dots are from my tests on damage reduction, how much the damage actually decreased at those levels. And you can see, you get somewhat less damage reduction than what it says you do. So what I expected here was an equation like the top, where you modify damage, you take your raw damage, you multiply it by 1 minus that damage reduction factor. So if it's a 20% damage reduction factor, you multiply your damage by 0.8. That takes 20% of the damage away, and that's how much damage you take. They seem to have coded something somewhat different, which is instead you divide the raw damage by 1 plus the damage reduction factor. So instead of multiplying by 0.8, you divide by 1.2. Personally, I think they did this wrong. in terms of game design, they can build the game however they want to. The thing that I'm angry about as a mathematician is that they called this percentage reduction. This is not a percentage. What you're doing isn't a percentage, because when you get to 100%, it doesn't do 100% effect. That's not what a percent is, so you should call these damage reduction points instead of percent. And that's why this really threw me for a loop. I did not expect this. So here's a quick example. If you have damage reduction of 20% and you're taking 300 raw damage, what you're going to get is 300 divided by 1.2, which is 250 total damage. So note, although your character sheet might say 20% damage reduction, the actual reduction in the damage is 16.67% in this case. Again, this is why, as a mathematician, I think this is wrong, but this is the mechanic as implemented in the game. Here's a chart showing my results. So the blue dots here are my projection, using this formula that I'm pretty sure is what happened here. This is what the curve should look like. The red dots are my actual observed data points, so you can see they are just right on top of that projection. So I'm pretty confident this is exactly how the damage reduction formula works. So after accounting for that, then my defense versus damage curve stopped having that weird bump at high defense values and looked like this. So this looks like a nice sort of diminishing returns curve. And so the question is just, what is the shape of that curve and what are the parameters of that curve? So my first hypothesis is that this is an exponential decay curve. So an equation of the form 1 minus e to the negative defense divided by k. So some k value that is essentially every some number of defense, every 10,000 defense, you cut damage in half or something like that. And so I tried throwing that hypothesis up against the actual data that I had. And while it fit the data fairly well at these lower levels, you start to see as defense got large, the dots get sort of lower and lower away from that curve. So that is not what the damage reduction formula is. So hypothesis number 2 here was that it's a capped exponential decay. So roughly that same formula. There's still that factor of e to the negative defense over k. But then you take that whole thing and you multiply it by some limit. So you basically say, it's not possible for defense to reduce damage by more than 90% or something like that. And you add that limit factor in there. I'll spare you all the agony that I did in the spreadsheets trying to find these exact parameters. But here is the curve that I came up with some specific values for that limit and that k. And you can see, once again, the prediction lines up pretty well with the real world data. There's a couple data points that are off by like 1 to 3%. Most of these are well under 1% margin of error. So maybe I just screwed up a couple of those samples that I gathered. But again, this seems to match with reality pretty well. So the best fit curve that I was able to come up with was a limit of 0.59 and then dividing defense by 10142. So just plug defense into that, and it should give you a damage reduction value, something between 0 and 0.59. And that's the amount of damage that you can knock off the attack. So like I said, the average error versus my observations in this case was 0.71%. So this was pretty good at predicting the values that I got up to the limit of where I was able to observe things. An alternate version here, I suspect that the code actually probably has some rounder numbers than those ones. So here's an alternate that uses nice round numbers, 0.6 times 1 minus e to the negative defense over 10,350. That may be the actual value in code. Whereas the last formula had an error of 0.71%, this one is at 0.76%. So a little bit more error. But if we look at the curve for this, it looks pretty much just like that last one. The blue dots, form a nice curve that looks just like the red dots there. So what this means, that factor of 0.6 is worth noting. So that means it is not possible with defense alone to reduce your damage by more than 60%. So no matter how high your defense gets, it can only get up to 60%. As far as I know, the damage reduction formula can get higher than that. You've got to get to a pretty high amount of damage reduction to hit that. There may be a cap there. I wasn't able to test up to those values. My tests only went up to about 40% damage reduction because that's what I was able to do cleanly in my experiments. So it's possible that the formula changes at higher values, and I just can't witness it yet with the data that I have. So what are the implications of these particular mechanics? First of all, so there's a decay in damage reduction. Every point of damage reduction is not equal. Your first points reduce your damage pretty substantially. Later points add less and less. And so, for instance, we have an example here. If you're at 30% damage reduction, that means, according to the chart, you're taking 76.9 points of damage for every 100 raw damage that's dished out. If you add 1 point, so go from 30% to 31% damage reduction, then that 76.9 becomes 76.3. So that is less than 1 percentage point reduction, but since your initial damage there was 76.9, the reduction from where you already were is 0.76%. And so this column here on the right I have listed as effectiveness. That's essentially how effective is that next point of damage reduction at reducing your damage. But essentially, the more damage reduction you get, the less effective it is. And so I look at this at kind of the points that are somewhat significant to me. At 50%, you're at basically 2/3. So at 50%, you've taken away 1/3 of the damage, but each additional point is only going to be worth 2/3 as much as it was before. At the 200% mark is where you get down to 1/3. It's only 1/3 the effectiveness of what you had, for the first few points. Defense similarly has a decay curve. Your first few points of defense reduce your damage significantly more than higher values. And so, for instance, here we see at 2,000 defense, you're taking about 10% off the damage. At 4,000, it's a little less than 20%. And so between 2,000 and 4,000, the difference isn't huge. Still, 2,000 equates to about 10% more reduction. But if you see, then you have to add about 4,000 more after that, and 4,000 to 8,000 to get to a little bit more than another 10%. And so that's where you start seeing the value of 1,000 defense dropping off pretty quickly. In the ballpark of 18,000 defense is where you hit 50%. Where you're taking off half the damage with the defense factor. At that point, your effectiveness is dropping pretty quickly. So again, since the max is either 59 or 60%, then pushing your defense up above that, it's hard to get additional damage reduction there. And so if you're up all the way at 40,000 defense, which I can only theorize right now, I definitely do not have any heroes that are anywhere close to be able to achieving that. But you're only at 5% effectiveness. It takes 20 defense to have the impact that 1 defense would have had back at the initial part of the curve. And so if you're looking just to extend survivability for your champions, you've got 3 different options to look at. The first one is increasing HP. The nice thing about HP is there's no decay curve. 10% more net HP is always 10% more HP. Note that doesn't mean that a piece of equipment that says 10% HP is always 10% HP, because that's 10% of base, not 10% of your current modified value. But more HP is always more HP. Your second option for increasing survivability is increasing defense. That becomes somewhat less effective beyond about 10,000 and drops off significantly after about 20,000. Obviously, more is always better, but with diminishing returns as you get higher into the curve. And method number 3 is increasing your damage reduction percent. So that one, similarly, it's somewhat less effective beyond 50%, and it's significantly less effective after 200%. I'm not sure if it's possible to get more than 100%. I theorize it is, based on the values that I've seen in equipment so far, and knowing that there's equipment several notches better than what I've found so far. But yeah, if you push up above 100%, you're definitely in diminishing returns territory there. Finally, I just wanted to throw out some interesting equivalences. 0 defense and 15% damage reduction is the same as 2,550 defense with 0% damage reduction. Similarly, 2,000 defense with 15% damage reduction is equivalent to 4,000 defense with 0% damage reduction. And so, at that point, just grabbing that 15% factor is worth doubling your defense at that point. So combining those can be worth a lot. And I think the last example really shows that combining the two is the most effective. You can get, I believe this figure is almost 50% reduction here. So you can get that from 20,000 defense, you can get it from 105% damage reduction, or you can get it from 8,000 defense plus 40% damage reduction. So, if you don't go for exclusively one or the other, but you mix them together, that multiplicative factor of getting both at the same time is going to be the most effective. That's it for tonight. I hope, especially for a lot of you spreadsheet nerds out there like me, you appreciate having these formulas and being able to use them as you try to optimize your heroes. Thanks for watching. If you enjoy mathematically based min-maxing analysis and advice, I would love for you to drop a subscribe on my channel. That's it for tonight. JG out.